All right, here we go with section 4.2, logarithmic functions with me, Mr. Hain. All right, so logarithmic functions. What are they? These functions are the inverse of exponential functions. So as we mentioned at the end of our exponential functions video, logarithmic functions are the inverse. And so let's start with what we know or see what they are right now. So we have a log, the b log of x is equal to y. So b is the base. It's written subscript, so below the regular text, you see x and the log are on the same line. If I was writing on lined paper, the b would be slightly below it, just how an exponent would be slightly above it. X is the answer to the exponent, and y is the exponent itself. So if I were to rewrite this, we can rewrite any logarithm as an exponent. Kaboom. What does that look like? That looks like this. I can take these elements of a logarithmic function and rewrite them into this exponent. The base of the log is equal to y, which is the exponent, and x is the answer, or the simplified form of that log. So really, what logs let us do is they let us use the number that we want and the base to find the exponent of a number. So we're going to look at a lot of different examples. First, let's rewrite some logs and apply what we know about this property here. So we can rewrite any log. So let's rewrite them. So we have checkpoint 1a. The 7 log of x is equal to 3. Of course, 7 is the base, 3 is the exponent, and x is the answer. So 7 to the third is equal to x. The b log of 25 is equal to 2. And of course, that means b squared is 25. Many of you are probably screaming at the screen. B must be equal to 5 or negative 5. You are correct. We have the 4 log of 26 is equal to y. Or 4 to the y is equal to 26. Now that's some decimal. We don't know what power of 4 would equal 26. 4 squared is 16, and 4 to the third is 64. So it's going to be somewhere very close to 4.2 something. And now we have what is really scary looking. The 3 log of 7 is equal to x plus 2. Don't get weirded out, ladies and gentlemen. This is just 3 to the x plus 2 as an exponent is equal to 7. All right, so that was going from logs to exponents. So let's take a look at exponents to logs. Now remember, 2 is the base, x is the answer, and 5 is the exponent. So of course, it's the 2 log of x is equal to 5 for checkpoint 2a. Here we have b to the third is equal to 27. Many of you are probably screaming at your screen that b must be equal to plus or minus 3. You are correct. However, that is the b log of 27 is equal to 3. For checkpoint 2c, e to the y is equal to 33, or the e log of 33 is equal to y. Now I'm going to come back to this later, either in this video or another one, but you can rewrite e log as the ln, which is also a key on your calculator. So the ln of 33 is equal to y. And we have another scary one. This looks like x to the 4 as x plus 4 as a quantity to the 7th power is equal to 12. And really that just means that x plus 4 log of 12 is equal to 7. Excellent. So this is rewriting logs or rewriting logarithms. So now let's evaluate them. If we're evaluating logs, really we just want to find out what they're equal to. So this log says the 2 log of 16 is equal to what number x? And of course, 2 to the x is equal to 16. Well, I know that if I raise 2 to the 4th power, that is 16. So the 2 log of 16 is actually equal to 4. So the 3 log of 9, or 3 to the what power is equal to 9, of course, we have to raise 3 to the 2nd power to equal 9. Now I'm going to mess with you here a little bit. The 25th log of 5 is equal to a number x. And of course that means 25 to what power is equal to 5. Now if this was the other way around, many of you would say 5 squared is 25. So we have to figure out a way to make it the opposite of 5 squared. Of course, the opposite of 5 squared, or undoing 5 squared, would be the square root, which is a fractional exponent, which is, yes, the 25th log of 5 is equal to 1/2. So continuing to evaluate logs, we're going to look at the 10 log of 100. Now this really is simple. It just means 10 to the x power is equal to 100. And of course that would be 10 squared. The 3 log of 3 is equal to a number. This is getting really interesting, and it's going to lead into our next slides here, because what we're saying is 3 to the what power is equal to 3. That would be 3 to the first power is equal to 3. And our final example here is something much like C. So 36 to the what power is equal to 6. Looks just like our 25 to the what power is equal to 5. And of course, if you're screaming at your screen, 1/2, 1/2, 1/2, you are indeed correct. It is 1/2. So let's talk about these logarithmic properties involving 1. So the b log of b, whenever you see this, just as in our previous slide, we saw the 3 log of 3. Whenever we see that pattern, we will know that it can only equal the number 1. And so the b log of 1, no matter what the base is here, can only equal 0. Any number to the 0 power is going to equal 1. So, I mean, the b log of 1, b being any base, has to equal 0. So the inverse property of logarithms. All right, so let's examine this log. The 3 log of 3 to the x is equal to y. All right, what the heck does this mean? So if I'm rewriting this, I can actually rewrite it as an exponent. I can say 3 to the y, this base to this exponent, is equal to 3 to the x. What? This seems a little bit fishy because you'll see that the bases are the same. So that must mean, therefore, that y is equal to x. Or put another way, the base of any number, or any number raised to the base of the same log of x is equal to x. So with numbers, 3 to the 3 log of x is equal to x. So again, it could be 3 to the 3 log of 1.5, and then this would have to equal 1.5. So 3 to the power 3 log of anything will equal whatever that logarithm is taking, or whatever the log is for that. So always and only is equal to x. So let's check this out. The 7 log of 7 to the 8th must equal, if you're screaming at your TV screen or your computer screen, 8, you are absolutely correct. So the 5 to the 5 log of 17, and again, this is what we were talking about here. If you're screaming at your screen, 17, you are correct. All right, so let's talk about the graphs of logs. So if I'm talking about the graphs of logs, it's the inverse of b to the x, and we reflect the exponential function over the line y equals x. So we're going to start with where we know. You might recognize this graph from a previous video for section 4.1. This is the graph of the line y equals x. It's a little bit rough. I'm just using PowerPoint here, so I'm just drawing the line across. And of course, if the inverse is reflecting that, if I take the fraction here, I'm actually just reflecting b to the x over this blue line. So there we go. It must be this line here, or I'm sorry, this green line over this line here. Excellent. And if I take the base of the log is greater than 1, I reflect the red graph over the blue line, and I get this orange line here. Excellent. So what do you realize about the domain of a logarithmic function? So unlike the domain of an exponential function, which is any real number, negative infinity to positive infinity, we see that this asymptote in the exponential as it approaches 0 is actually reflected or over the y equals x axis, which gives us this asymptote here, which is the y axis. So there is a restriction for x, and if you are actually screaming at your screen, it must be greater than 0. You're correct. The domain of a logarithmic function must be greater than 0. So I can ask you questions about the domain of a logarithmic function. So, for example, what is the domain of this logarithmic function? So I got to take x plus 3. I don't care what the base is. I just want to take x plus 3. I'm going to set that greater than 0 because I know that the graph must be greater than 0 right here. So I'm going to set it greater to 0. I'm going to solve for the x, and I know that x must be greater than negative 3. So check it out. To find the domain of logarithmic functions, all I'm going to do here, and I want you to try this one, is I'm going to take part of this logarithmic function and set it greater than 0. Yeah, that's the 2x plus 8 part has to be greater than 0. So I'm going to isolate x by moving the 8 to the other side of the inequality and dividing by 2. So now I have the domain of f has to be x greater than -4. Awesome. Let's take a look at another example. So I have the 10 log of -3x minus 18. So I take the what I'm taking the log of, -3x minus 18, set it greater than 0. Add 18 to each side, isolating x. And of course I have to divide by -3. And when I do, it changes the direction of the inequality as you see here. Excellent. So the domain of g is x is less than -6. Awesome. So here is the domain of different logarithmic functions. Awesome. So we're going to keep on moving, and we got to talk about common logs and your calculator. So if you've noticed is that a lot of my other slides have had like the 10 log, the 7 log, the 5 log, the 4 log, but if you look at your calculator, there is no base. And of course that implies a base of 10. And I said that I would come back to it later in this video, but the e-log can be expressed as the natural logarithm, or the ln. So ln just means that the base of that log is e. It's a different way to write it so that we can see immediately that we are dealing with, again, functions that are probably going to ask us to consider exponential growth and decay. And so the base here, e, can be just written as the ln. So let's use the logarithms in formulas. So I'm going to give you guys two formulas. They're going to be really cool. I like them a lot. They're given in your text as well. B to the x is the percentage of adult height by a boy, x years old, and g of x is the percentage of all adult height by a girl, x years old. Now, if you're like older than the age of 18, these probably won't work for you, or your numbers are going to be somewhere 90 or even over 100. That just means you've stopped growing. But if you have a young one in your life, like your niece or like a niece or a nephew, like I do, then you can use this function b of x, which models the percentage of adult height by a boy, x years old. And I can use my nephew as an example. Now, my nephew at the time of this recording is 12 years old. So I plug in 12 to this part of the function. Now, 12 plus 1 is 13. Now, using my calculator, I can evaluate that function and find out that he is actually 83.4% of his adult height. He's got room to grow, and he's 12. This guy is going to be growing tall. And I can use the same idea to model the height of my niece. So this is the function g of x is equal to 62 plus 35 log x minus 4. Again, this implies immediately that we can't have any idea how tall a girl will be until after the age of 4. And she is 8 years old. So 8 minus 4 is definitely 4. And using the power of my calculator, she's reached 83.1% of her adult height. Sadly, this means that according to these formulas, my 8-year-old niece is almost the same percentage of her adult height as my 12-year-old nephew. She's going to be shorter than him. That's basically what these formulas are saying. But that's okay. So that's logarithmic functions with me, Mr. Hain.